Log on, tune in, find out. Another good idea from Cambridge.
Q is 0 outside of some bounded open set D. D does not have to be connected, but its complement has to be connected. And we assume, so far we did not assume, but in the following we will assume that Q is strictly positive on D with a positive constant Q0 there. And so the wave equation is in our case a reduced wave equation, the Helmholtz equation in this modified form. 1 plus Q is the index of refraction, and U is a total field, and the total field is a superposition of the incident field. This is a plane wave of direction theta hat, and a scattered field, and the scattered field satisfies the radiation condition of Sommerfeld. Did not write that down here. And this radiation condition of Sommerfeld is kind of equivalent to this asymptotic expression of the scattered field. So the scattered field behaves like a spherical wave with a source sitting in the origin, some normalizing constant here depending on the dimension, and this amplitude function which we call far field pattern, which depend on the angle or the direction of observation. X hat is a unit vector in the direction of x, and theta hat is the angle or the direction of the incidence, plus lower order terms when r goes to infinity. So this is the data of our inverse problem. Given these data, we want to determine D, not all of Q, but D. We don't have to know the value of Q. That is also an important point. Maybe I forgot that to say that yesterday. We don't have to know the value of Q, but the factorization method is only able to determine the shape of D. And then maybe in the second step, if you know the shape of D, then you can try to figure out what the value of Q there is. And with these data, we define, and that is the essential point here, we define this operator, the integral operator, with our data as a kernel. That is a far field operator, and that maps L2 function on the sphere into L2 function in the sphere. Actually, the range space of F is much smoother because you can show easily that this is an analytic function with respect to x hat and also with respect to theta hat. And here also some properties of the far field pattern are known, reciprocity principle, and so I did not mention that in my talk here. And furthermore, an important property which will be needed and used in a moment is that F is a normal operator, so F commutes with its adjoint, and the scattering matrix I plus ik over 2 pi F is unitary. The other day I got a mail by somebody, not by you, by somebody else, reading my book and said, this is the wrong factor here. But the factor, of course, depends on the normalizing constant, gamma d there. Here. Okay, and then another notation here. So F is an important notation, that's a far field operator, and the other notation is this phi z. Z is any point in space. It's just this very simple exponential function e to the minus ik z times x hat, and that lives also in L2 on the unit sphere. So these are the notations, the repetition of last time, and then again a repetition here. We saw and we proved the factorization of this operator in terms of 3 operators: h, first h, then t, and then h star. I don't recall here the definitions of these operators because we first want to go into the functional analytic arguments. And also very important observation, or that this point z is inside of D if and only if this function I have shown you on the previous slide is in the range of this operator h star. Okay, so that gives you a characterization or a translation of the domain into a range condition there. Okay, and so this was the picture, the last picture from yesterday. We have this general situation, 2 Hilbert spaces, F maps here, H, T, H star, and that diagram commutes. And now we can try to find several theorems or results how to relate now the range of H star by F. F we know, H star depends explicitly on D, we do not know. So we need to express that by F. And this is the first theorem, which is kind of simple. I gave you an idea of the proof yesterday. If T, this operator, is self-adjoint and coercive, then the range of H star is the range of the square root of this operator F. So if you know F, you know the square root of F by an eigenvalue decomposition of F. Yeah, if T is self-adjoint, then F is self-adjoint. So this is not the case in our scattering problem. Only in the Born approximation, F is self-adjoint, and then you can apply this theorem. And if you combine this and that, you get that Z is in D if and only if this function Vz is in the range of this known operator F square root of F. No? Okay, now we come to the theorem which applies to our nonlinear scattering problem where F is not self-adjoint. So this is the basic theorem here. Assume you have two factorizations. F has a factorization in terms of H1 star T1 H1 and also in H2 star T2 and H2, such that the middle operators T1 and T2 are coercive in this generalized sense. So they are not self-adjoint anymore. So what you do is you take the inner product, or this quadratic term, Tj phi phi, which is in general a complex number because Tj is not self-adjoint anymore. But you take the absolute value of these complex numbers, and it's possible to estimate that from below by a constant times the norm of phi square in this space xj. For all phi, you only need to have it in the range of this operator hj. Then you know that the range of this operator is the same as the range of that operator. So this is the basic theorem we will apply to our scattering problem, but it's a purely function analytic theorem. And so here the idea of what you do for the proof. So I somehow formulated it with respect to the inf condition, but maybe more elegant proof is by Nachman, Peverinter, and Tarela. If let H be one of these two spaces, H1 or operators H1 and H2, the first line, that is the essential estimate actually. A function is in the range of H star if and only if there exists a constant such that you can bound this F, which is H star Th, this quadratic form is bounded not by psi, but by the kind of inner product between phi and this test function psi in the norm of y square. No? Assume at the moment you have this equivalent there, then you see the next two are then pretty obvious. If you have that, then you can also say, okay, I keep that fixed, maybe to be 1. Yeah, I only take those psi such that this is 1, and I try to minimize that. And that can't be 0. No? It should be bounded below. No? So you see that this is apparently equivalent to that one. Or you can take the other way around and say, okay, I take only those psi such that this is 1, and I maximize this, and this is this subcondition there. No? So you see these two, the inf condition and the subcondition, they really are special cases and follow from this easily. So I want to go a little bit into the proof of this basic theorem, and in particular I want to show you that this is needed there, this coercivity condition, because that is the severe restriction to apply the factorization method to other more general situations. No? Unfortunately, we would like to have a theorem, and my the previous speakers also, gave you homework assignments. So weaken this condition, and still prove something like that. That would be a very important step forward in the application of the factorization method. So let us look at that. First of all, the simple argument is the following, going into this direction. Yeah? So we assume that phi is in the range of h star. So assume that phi is h star of, say, this kind of phi. And what you do is, I start with the right-hand side and look at f psi, and of course I plug in for f the factorization. So it is h star t h psi. So very, very simple. Now you put the h star over. I mean, that's the definition of the adjoint. So you get t h that h this. So this is of course in the space y, and this is now in the space x, but I dropped that. Okay, now you use the coercivity of t. No, this is the argument. So you have that this is constant, or this constant c here in the coercivity, and this c is not the same. I mean, they are of course different. So then you have c norm of h psi, just by the coercivity. And now you use a little kind of trick. You write it this way, divided by this phi square and multiply that again. And now you see here, you apply the Cauchy-Schwarz inequality, but the other way around. So this is less than this factor. And here you have, say, phi h psi. So Cauchy-Schwarz tells you this is less than that. Now you put h over again, and you have c, and then you have h star phi, but this is phi again. So we get that, and this is a constant now you put to the other side. Okay, so you see that is very kind of very simple, just one line. Now the other, I don't, probably the other direction is a little bit more complicated, maybe. Assume it's, maybe you can find more elegant proofs as I did, but assume that now phi is not in the range of h star. Make a proof by contradiction here. And you define the space V as a space of all psi such that phi psi is 0. So this is the orthogonal complement of phi. And then it is easy to show that now the image of V under the map H is dense in the range of H, in all of H. And here you need that phi is not in the range of H star. You show, or at least I did it, I showed that the orthogonal complements are the same, of that and that. And okay, now we as we know that, we can find, how do we do that? Now we can choose, find a sequence, say psi j, such that h of psi j converges to right to h of phi over, I think, phi square. Yeah? So this is in the range of h, and these psi are in V. So by this. Okay, and now you set psi j is psi j tilde, or say minus here, plus phi over phi square. What do we have now? Now we have, if we multiply it by phi, then phi of that is 0, because this is in V, and phi multiplied by this is phi square over that is 1, right? And now we now we look what is f psi j Yeah, we have that already there on the other side. This is this part. Yeah. So we can estimate that by norm of t times norm of h psi j, but this, if you look at this, that tends to 0. Because h of psi j is h of this, and that tends to minus this. So that tends to 0. So we have seen this is a contradiction. No, we have seen that is 1, and that goes to 0. It can't be. Okay, so this is my way to prove it. You did it differently in your paper. Okay, so let us now apply that theorem to the scattering problem. So recall we have a factorization of h in the form of h star th. Okay, this is still a general theorem. It's still a function analytic theorem, but it is modeled really. I mean, it's to our scattering problem. So now we have the same situation, and in addition we assume that f is, or that I plus IRF for some r is unitary, for some r positive. In our application, r would be k over 2 pi. Furthermore, let T be a compact perturbation of a self-adjoint cursive operator, and the imaginary part of that is not 0 for all phi in the closure of the range. Then the range of h star is a range of f, but here the absolute value of f power a half. So how is that proven? First of all, the assumption, the assumption that that T is a compact perturbation of a coercive operator plus this condition, that implies this general coercivity condition. That's also kind of a simple function analytic argument. If you have a compact perturbation of a self-adjoint coercive operator, and you have this additional condition there, then you can prove this generalized condition here from this is satisfied. Okay, this is the first step. And the second step is f is normal. That follows from the unitary here. And as you know from function analysis, a normal operator has a spectral decomposition, just as the adjoint operator, with the exception that the eigenvalues are not real anymore. Okay? I'm sorry? No, my operator I should maybe have said it somewhere, it is compact. Yeah? H is compact operator, so F is a compact operator, so it has a discrete spectrum, and it's one-to-one, and you're right, I have to add here compactness of that. Okay, so F is normal, and there exists a complete orthonormal system of eigenfunctions and eigenvalues. Furthermore, so you can write down what F is, and you can define now, this one is now defined, for example, by the spectral decomposition. You take the complex eigenfunctions, eigenvalues here, take the absolute value and the square root out of that, and then this middle operator S is just the face of this complex eigenvalues, no? So it's lambda j over that, and this is of course self-adjoint operator here, and so you have this and that. No? If you just plug that in, you see it immediately. No? Yeah, in the self-adjoint case, this would be the identity here, no? Because that would be 1. Okay, so here I plotted the situation. The fact that the identity plus I RF is unitary means that the eigenvalues of this operator lie on the unit circle in the complex plane. Unitary compact operators, unitary operators, sorry, with a discrete spectrum. It can't be compact, of course. They lie here. So this is a translation of this operator. F is a translation of that operator. So the eigenvalues of F, we are talking about the eigenvalues of F here, not of that. They lie now on this circle, with center on the imaginary line because of this I, R, and R is real. And of course this circle has to pass through 0 because F is compact, so the eigenvalues tend to 0. So okay, so the eigenvalues of F, these lambda j, lie on this small circle. Okay, and also we know from essentially from no, nothing else, first of all. Okay, now we look at these quantities, we normalize them, yeah, and so that means normalizing them, we put them on this is a unit circle here. So they lie in the upper unit circle. If you project them from the 0 to the unit circle, they lie in the upper part. Now, first of all, you don't know, and that's the crucial point, the eigenvalues lambda j on this circle here, they tend to 0. But first of all, you don't know how they tend to 0. They can tend to 0 from the right-hand side, from the left-hand side, or they can kind of oscillate. First of all, it's not clear. But the property, again, that T is a compact perturbation of a self-adjoint incursive operator tells you they have to go from the right-hand side to 0. Yeah, so here they start somewhere here. 0 is not an eigenvalue. They start here and they go, and then from the right-hand side they go. That follows from this compact perturbation of a self-adjoint coercive operator. Okay. Now, now we can look. We have two factorizations now of F. One is given by the previous stuff, and this is the other factorization by a spectral decomposition of F, essentially. Okay, so we have this generalized coercivity of T. I said that before. We have to prove this generalized coercivity of S. And that means we have to say, can we bound that below by this? No, this is a generalized coercivity. Yeah, please. No, sorry. This was this calligraphic S. This is just defined by this. This is a definition of S, my S which appears here. Okay. But now this is a nice kind of geometric argument. Assume you take psi which have norm 1. Yeah? Norm 1 means that the sum of the Fourier coefficients are 1. And now, assume that the sum of these parts here, sum of the Fourier coefficients square, are 1. That's Parseval equation. The Fourier coefficients are the same as the norm. Okay, so you have here now a convex combinations of these complex numbers. These are complex numbers, and if the sum of the coefficients here are 1, then you have a convex combinations of complex numbers. And these are the complex numbers here. They go, the complex numbers, these normalized, they go from there and converge to 1. Because, okay. And what you want to do is you want to minimize that with respect to all convex combinations. So that means you want to find, you look at the convex hull of these things. All convex combinations of these complex numbers they form the convex hull. What is the convex hull of these projected eigenvalues? This is, you have to kind of draw here a line going through that and that point in that picture, and the convex hull is then this part of the half of the half plane. Okay, and then bounding that below by some constant means that this line does not go through 0. So you can bound that. So the distance of the convex hull to 0 is positive, and you see that from this picture. But you see also, you need really heavily that the eigenvalues tend to 0 on one side here, and if they go, if they oscillate and go to 0 also from the other side, then the convex hull would be just the upper half disk here, and this would not hold. And that is the point why other applications of the factorization method do not work. I will mention some examples later on. Okay, so this is a sketch of a proof of that theorem, and now we can just apply that. Again, we have to assume that k square is no transmission eigenvalue, because then the f is 1 to 1, and that is unitary. We have this operator t here given in this form. Is not so important at the moment. And what we can show, it's a compact perturbation of a cursive operator. Oh, it is, of course, important. What is the equation for v? V satisfies the kind of Helmholtz equation, delta v plus k square 1 plus q v is equal to plus or minus, I've forgotten, k square. This v is a radiating solution of that. But here you see the operator t is essentially f goes to this, q is bounded below, so the first part would be coercitive, is almost the identity, and this v, the mapping from f to v is compact. Here, if you have this elliptic equation, f, if you map the right hand side of that into this, this is continuous from L2 into H2 in the Sobolev space H2, which is compactly embedded in L2. You restrict yourself on D, so you have this compactness property here at that point. So also Green's theorem, if you do it a little bit careful, also shows this condition on the imaginary part of that, and so you get this condition again, and you have that from the previous from the previous slide. Now we can combine that this result with the previous one. recall this function again, and we have now that z is in D if and only if this function is in the range of this operator f. So what you have to do is, given your f, you have to do a spectral decomposition of f, then you have this operator here, and you have to check on the range if that function is in the range of that. Yeah, how we do it here, again, lambda j are the eigenvalues of this operator f with normalized eigenfunctions. Then yesterday at the end I cited Picard's theorem, which is one of the basic theorems in inverse theory, characterizing the range of an operator. Range of an operator is characterized by a certain decay of the Fourier coefficients with respect to the eigenfunction, or in general the singular system. So here you have, because of this half, you have only here factor 1. Here's 2, the Fourier coefficient squared, and here just this. And also you can do it this way, taking the inverse of that, and that is 0. 1 over infinity is defined to be 0 in this setting. I very briefly want to just sketch the idea what to do with if you have absorption. So if the imaginary part of Q is not 0, but it's real, if you have absorption there, then you have still the factorization, but you have f is not normal anymore. So then the whole nice thing with the spectral decomposition breaks down. And it took a while, and now we know how to handle that problem. We define the kind of the real part and the imaginary part of the operator f, just as you do it for complex numbers. Yeah, and then of course, if f has this factorization, then also f star has a corresponding factorization, and you have the factorization of that and that, and you define f. What is it here? Twiggle? No, sharp. F sharp. F sharp by kind of the absolute value of that. Again, this is a self-adjoint operator now, so you can again define that part by spectral decomposition, and you add the imaginary part. So you apply the whole thing on this operator instead of f. This is a self-adjoint operator now, and the hard part is now to prove that also this has a factorization with the same h here, but with some operator t tilde. The difficulty comes because of the complex of the absolute value here, of that. But you can do that, and then you have this theorem, the same kind of theorem, but now you take the eigenvalues and eigenvalues of the square root of this operator instead of the operator f itself. Yeah, before I come to numerical results, I want to briefly show you the connection to the linear sampling method, because the linear sampling method is maybe better known to engineers also. They apply the linear sampling method, and although it is not more difficult to do the factorization method actually. So recall the factorization method. The phi z in the range of f means that this equation is solvable in L2. No, that is the range condition for this operator. I wrote it in terms of an equation. We have seen that. Going back to the case that f is normal. Otherwise, you have to replace that by this f sharp. The linear sampling method, they look at this equation with f itself, right? So they look whether or not this is in the range of f and not in the range of the square root of f. This is a difference, just the only difference in implementing the method. If you implement that, you can easily implement that. It's not a big change. Of course, if that is solvable, and if you plug in the our factorization of f in this form, then you see that also this is solvable with this operator there. Just take that to be h. Therefore, phi z is in range of that, and thus z is in D. So, but the other way does not work. If z is in D, then this does not have to be solved. And that is the main drawback of the linear sampling method. It only discovers, the solvability of the equation only discovers a subset of D. And if you look at the case of a ball, then actually this is solvable only for the center of the ball. So in theory, you cannot really determine the domain from solving this. You have to solve that equation in order to get, in theory, the correct result. But nevertheless, this is used very often, and they regularize that by Tikhonov regularization and so on, and get comparable results. But from the mathematical point of view, that is not so nice. But if you regularize this, and that is a fairly recent result, if you regularize that equation by Tikhonov regularization, you probably know, then you have epsilon identity plus f star f of g times this. Now, and you always can solve that equation, even if that is not solvable. Even if the kind of original equation is not solvable, this equation is always solvable. If you know anything about inverse problems, then you know this. And this g depends on the point z and also on the regularization parameter alpha. Okay, now let Vg be the Helmholtz function which with kernel g. This is the Helmholtz function appeared in other talks as well. Vg is just you take the these are just the superposition of these plane waves. This is called Helmholtz function with this kernel. So so if you can show the following. If x is in D, then you can solve the factorization method. This is solvable, no? And this is my hz here and there. And you can, of course, do that always. You can solve this equation always. And if epsilon tends to 0, then this limit exists and lies in between that and that. However, if x is not in D, then this limit or this function, you look at the Helmholtz function at the point z, not in any point, but at the point z. So then this goes to infinity. So kind of plotting this limit would also give you a criteria whether or not the point is inside or outside. If this limit is bounded, limit is finite, then the point is inside. If the limit is outside, then if the limit does not exist, it goes to infinity, then the point is outside. So with this interpretation, you have also kind of a precise proof somehow that the linear sampling method also works. But also the linear sampling, this theorem is only true for those situations where the factorization method works. And then you can take the factorization methods right away. Okay, last slide in this talk, connection to time reversal. I discovered that only recently, although it's pretty clear. There's a paper by Hazar Ramdani, 2004, and many other papers on time reversal in frequency domain. We have heard by Gunther Ullmann time reversal in time domain, but here it's in frequency domain. R is the kind of the inversion operator, reflection. You make the complex conjugate and kind of reflect x hat. Then my f goes from g to fg. Then I apply this operator R, apply f again, Yeah, this corresponds to, you know, sending it back on the into the other direction again, no? My R. And then I apply F again and then reverse again, and it's easy to see that R, F, R, that is just the F star. So this time reversal operator is not F, but F star F. Okay, the idea of here of time reversal is that we take the largest value or lambda of F, I guess it is maybe missing here F star F, and the corresponding eigenfunction, and plot this Herglotz function here with this with the eigenfunction there. Yeah, and then you can easily prove that this Herglotz function at that point z could be written in this form. There's also kind of Green theorem and yeah, and so you see that the Bessel function here that decays if you go away from that, from z. Yeah? So if y is away from that, so, yeah, so y is in D. So if z goes away from D, then it decays. So in this way, this function focuses on D. So what they do is they plot this function with respect to z, and then you somehow see the domain. How is it related to the factorization method? We also take yeah, here it's correct. It's lambda of f, assuming that f is normal again. Yeah, in that situation. Yeah. So the factorization method would be taking. Yeah, okay. The Herglotz function there is nothing else but the inner product of this phi. This is the complex conjugate of my phi function, phi x, times this. No? So this is the observation there. So what the factorization method is, we take this here for all, not for one eigenvalue, but for eigenfunction, but for all of these eigenfunctions divided by lambda 3, and take that and plot that, or the inverse of this. So there's a kind of interesting connection. They take here the largest, and they argue that if you take the largest eigenvalue here, you see the largest component of your scatterer. If you take the second largest, then you see the next one, and so you can build up the one. Here, all of these steps are kind of combined in plotting that. Okay, so I want to show you some numerical simulations, and I even have prepared a MATLAB code that you see how fast that is. But that will be done in the next lecture this morning. Thank you very much.